Hey guys, welcome back. Our next lesson is Trigonometry with Radians. And yes, that exclamation point is necessary. Our mindset message for today is that everyone was made to do math. And I say made on purpose. God created us to think in these ways. Some of us are more on the creative side, some of us are more on the logical side, but each of us has a contribution to make to the discipline of mathematics. Our learning goals for today, we're going to define what is a radian. I know you don't even realize what that is yet. Don't worry, we'll get there. And we're going to connect radians to degrees. Okay, there's a very specific way how these connect. Essentially, they're two different ways to express an angle's measurement. And then we're going to relate the motion of an object around a circle, kind of like we saw in our recent lesson, but to trigonometric functions. Prior knowledge for today, pretty much, is the sine and cosine ratios, remembering what those are, and some vocabulary from geometry for circles, which would be a central angle and the arc of a circle. So let's dive right into our initial core idea for today's lesson. So we've got a circle here, and let's just say typically we're going to be working with a unit circle, which means we're going to assume that the radius of the circle is 1. All right? There's something really important here. There is a direct correspondence between the central angle measurement, okay, that would usually be in degrees, right, and the corresponding arc length. So here we've written out that central angle, and we usually use in trigonometry, the general variable to use for the angle is theta. Theta. It is a Greek letter. And then the corresponding arc length. I've labeled this point x, and then this point where the angle actually finishes. So you want to imagine starting here at the positive x-axis, and then opening the angle up this much. Okay? And I've labeled that. In fact, we can even draw that in there too. Okay? And so that arc, that section of this circle's circumference, we've called xp. Now the interesting thing here is the actual angle here in degrees is of course a certain portion of 360, right? And that represents a full rotation. But also, this arc length is a certain fraction of the entire circumference of the circle. And it just so happens that these cover the same fraction of the rotation or circle, right? This fraction of 360 is identical to this fraction of the whole circumference. It's just kind of like blown up, right? So that's a really crucial key concept here, and let's dive into a few examples to apply this. So let's dive in and take a look here. So remember, this is a unit circle, means the radius is 1. So based on that, remember how we're talking about portions of the whole circumference? Well, if the radius is 1, recall that the circumference of a circle is, and I suppose actually I should have included that on our prior knowledge as well. So I'm going to add that in here. Circumference as well. So circumference is always 2 pi r, right? So since r is 1, the circumference here is simply 2 pi. So essentially what we're saying is any arc is always going to be some fraction of 2 pi, right? That means we can dive into this example number 1. For an arc length of pi over 6, what is the corresponding central angle? The key point here is that whatever the angle is going to be, it's going to be the same fraction, and remember angles are generally measured in degrees, right? It's going to be the same fraction of 360 degrees as this is of 2 pi. So maybe it's helpful for us to figure out what fraction of 2 pi is pi sixths. Why don't you pause right now and just think about that for yourself. We'll still come back and do it together, but I want you to think about that for yourself. How much of the circumference is pi sixth since the whole circumference is 2 pi? Go ahead. Okay, what you should have gotten for there is that it is 1/12 of that. Okay? Now, a way to figure that out would be simply to realize that, okay, well, pi sixths over 2 pi, that's essentially what we're saying. What fraction is it of it, right? And this is kind of messy and ugly, but if you actually remember some fraction rules, if you have a fraction on top, this and that end up multiplying. I mean, you could also think this is over 1, so you flip it, multiply, right? But either way, this ends up being pi over 6 times 2 is 12 pi, and that gives me 1/12. So I know that I have 1/12 of the circle covered. So again, going back, what is the central angle? It must be a 12th of 360. So 1/12 of 360. And it's important right now that we're using the degree symbol, especially because we're going to be thinking about degrees sometimes, and we're also going to be thinking about what we call radians, which we haven't defined yet, but we're going to soon. And a 12th of 360 degrees, let's see, 36 divided by 12 is 3, so this is going to be 30 degrees. All right? So, what we've done is looked at the correlation between this angle here, in this case 30 degrees, was equivalent to traveling pi/6 units around the circumference of that circle. Go ahead and take a stab at number 2 now. Okay, remember this thought process actually can be the same idea, but in this case we're starting with a central angle, so we can simply, 225 over 360, right? That's going to be, if we simplify that, let's see, divide both by 10 and we get 22.5 over 36, and then I multiply by 2. I'm going to be lazy here and grab my calculator. This is one I should have planned for. 5/8. Lazy me. So what we have here is 5/8 of the circle has been covered for a 225 degree angle. And that means we want to take 5/8 of that, right? So 5/8 times 2 pi is going to give me how much of that circumference, right? What that actual arc length would be. And this is literal length we're talking here, right? Looks like the 2 and the 8. Looks like I get 5 pi over 4 as my arc length. Okay? So again, right now we're establishing a connection between degrees, which basically we've used degrees just to think about the opening. It has not even had anything to do with the distance per se. But what we're doing right now is we're building a connection between degrees, which again is just kind of this vague notion of opening, to a literal distance around the circle. And since they have that correspondence with each other, then it's often more helpful to think about the literal distance and convert it to something that usually has pi in it. Okay? Let's take a look at a few other things now together. So now we're at the point where we can define a radian. A radian is an arc of length 1 on the unit circle. Okay? So it's simply an arc that has the length of 1 unit. Okay? And that's nice because we can think, okay, well, how many of those fit around the circumference? We already know that 2 pi r is actually the definition of circumference, right? So since we've just defined, basically what you can think of is you can think of taking that radius and then wrapping it around, like cutting that radius out and wrapping it around the circle, however far that is, right? So 2 pi radii literally will go around the circle, hence the name radians. Okay? Now, just like we saw, to relate degrees and radians, we use this proportion. D over 360 degrees, again we use that symbol when we're talking about degrees, equals R over 2 pi. And that can always be used to kind of find the corresponding angle measure. And the cool thing is, since there's that correlation, we're going to get to the point where we talk about trigonometric functions. Well, we can talk about the sine of an angle in degrees, or we can talk about the sine of an arc length with a specific number of radians, because it's like tomato tomato. So we can actually apply sine, cosine, tangent and those things to radians as well. And it turns out that's actually a much nicer tool for us to use, which is why we're introducing them today. So, next example. This is basically the same as we just did, but giving you more practice. So I'm going to ask you to pause the video and finish these guys off, and I'll give you the answers afterwards. Go ahead. All right, let's go ahead and give our answers. Pi thirds, I will just tell you is going to be equal to 60 degrees. Okay? Now again, using this proportion, you would get that. Something we did earlier though, just as a quick side note, was pi sixth. We already found that that was equal to 30 degrees, didn't we? Now if you think of pi sixth times 2, isn't that the same as pi thirds, right? It's double. And so it should make sense that 30 degrees doubled would give me 60 because pi thirds doubled, pi sixth doubled is pi thirds, right? Again, you could use this proportion if you like, but there's a little bit of a trick we could still use. If I already know pi thirds is 60 degrees, 4 pi thirds is simply just 4 of those, right? So this actually could be that times 4, which happens to be 240 degrees. Now, alas, part C seems like maybe we don't have a reference to something we've done before at this point yet, but we can still go ahead and utilize this proportion. 135 degrees. This is another one that I was silly and should have thought about and done ahead of time, although actually I should know this. Hold on. I'm just going to give you the answer. If you set up that proportion and you multiply by 2 pi, so 135 over 360 equals r over 2 pi, and that means r is going to be 2 pi times that ratio, right? But off the top of my head, I remember that 135 is, this is going to simplify to 3 pi over 4. Okay, my brain's a little bit rusty, right? So that's what you should get for that once you solve for r. And part D is a little confusing, isn't it? Wait a minute, this doesn't have any pi in it, but it doesn't have a degree symbol. Did Mr. Engel mess up? This is just put there for a reason. I want you to remember if you don't see the degree symbol, you can just assume it's talking about radians. So, fact is, we can still treat it like we would these, except we'd have to utilize that proportion again. Let me remove my little ball here. So again, what I'd have d over 360 is equal to 4 over 2 pi, if that makes sense. And that actually simplifies nicely, because then what I can say is d equals, this is the same as 2 over pi times 360, so that's 720 over pi, and that's not going to look any nicer than it does, so we're just going to have to say this is how many degrees, and I should have included that this whole time, right? So my bad. That's how many degrees it is, whatever 720 over pi is. All right, so now we're going to shift gears a little bit here, and we're going to dive more into some patterns. We all know that a circle, since this is based on the unit circle, a circle is the most beautifully symmetric object or, two-dimensional figure. And we're going to utilize that symmetry to figure out even more radian correspondences to degrees and even talk about the coordinate pairs that match them on the unit circle. Hey friends, welcome back here. We're going to move on to the paper actually. What I've done is I've drawn out a unit circle. This is kind of cool actually. I took a piece of paper and I folded it in half in both directions. And then I used a compass centered at the origin here to make a circle, and it looks real nice. Of course you can use the provided unit circle, but if you like to create things like I do and it's just satisfying, you can do what I did here too. So actually these are 3 more examples I want you to take a stab at yourself and pause right now before we move on to answering them together. So go ahead and pause. Let's answer these together now. What's the max y coordinate possible? Now we're talking about around the circle here, right? Well, I think it ends up being pretty clear that right here ends up being the highest point you can reach. And if we were to label this, and I've already labeled the origin here with degrees and radians, okay, so the left side would be my degrees, the right would be my radians, and then the coordinates that go with it. So right here the coordinates are actually just reversed from down there, right? So this is actually 0, 1. And if I do the degrees and radians for that, we may even take a look at that in a minute. But let's actually answer these questions and we'll get back to that portion. Max y coordinate is 1. Now, at what arc length does this occur? Well, actually, because I asked that question, we can get into this. I forgot. First of all, if the left is my degrees, I think we're all pretty clear how many degrees this is right here, right? You can also think it's a quarter of a circle, right? A quarter of 360, which of course is 90 degrees. Now, this is interesting. I think we can do this in our head without having to actually utilize that proportion. And because of the symmetry in the circle, we'll be able to fill in a lot of angles that correspond with different arc lengths. So how much of a circle is it? We already said that. Oh, it's a quarter. So if the full thing has circumference 2 pi, what's a quarter of that? 2 pi over 4, which simplifies to pi over 2 radians. So at what arc length does it occur? Pi over 2. Which arc length corresponds to 180 degrees? Well, again, remember, don't forget this. We're thinking about it as a fraction of the whole thing, right? So let's scooch a little bit over here so I can include the whole circle. And right here is 180 degrees, right? So we'll label that guy here. Well, if the full thing is 2 pi, and we can realize 180 is half of that, then this actually turns out to be simply pi radians right here. And again, we could label this coordinate here as -1, 0, and we could even keep going with that. But let's finish answering 6. Which angle corresponds to an arc length of pi fourths? This is tricky, but again, we can just think about what fraction of the circle that is. And if the whole thing is 2 pi, pi fourths is 1/8 of that. You could also go back to here. We already saw that this is pi over 2, pi halves, and pi fourths is going to be half of that. So what I can do here is say, aha, right now I'm estimating, but let's just say about there is halfway. And so this right here represents half of that, which of course is 45 degrees. But as far as radians go, that would be equivalent to pi fourths radians. And this one's interesting because this is why we've reviewed recently our special angles and stuff. I want to have you not forget something. There's a really important thing here, and there's a connection between the triangles we've studied in the past, okay? Because we're not just purely forgetting the triangles and only thinking about circles now. In fact, if you can imagine this point just moving around the unit circle and letting this triangle travel with it, if I had a point here, we'd have a triangle up there. If I move this point over to here, I could have a triangle that's kind of in the opposite direction as those other ones. And so actually it turns out that every possible right triangle that could ever exist, ever, actually lies within this unit circle if we think about moving this point around there like that. And in fact, it could be argued that they all lie even within one quadrant because they kind of just flip. Every one of these has a mirror image on the other side. And the only thing that's different here, if you remember our quadrants, is that our signs change, right? So back here, I have negative x coordinates but positive y coordinates. Over here, I have positive both. And then down in my bottom quadrants, these are both negative. And then over here, my x's are positive, but my y's are negative. So that can help us and the symmetry of the circle to finish filling all the rest of this in. So getting back to this, I think we've actually already answered what angle corresponds to arc length of pi fourths. That's going to be 45 degrees. And how about 7 pi fourths? We can utilize something we talked about already. This times 7 will work for that. So 45 times 7 is 225 plus 90, which is 315 degrees. So 315 degrees. And that's going to end up being somewhere in quadrant 4, which we can get to later on. So the cool thing about this is, now that I know these things, and one thing we've talked about here, if that's 1, we've actually talked about how this is root 2 over 2 in length, and this is root 2 over 2 in length. So this here, coordinate-wise, would end up being root 2 over 2, comma, root 2 over 2. Let's finish filling in quadrant 1, and then I'll ask you to fill in the rest of the quadrants on your own based on symmetry and just simply the fact that the only thing that changes if you reflect across there from these coordinates would simply be the sines. So let's go back here and let's actually do some other things. Let's, instead of splitting this into like 2 equal arcs, what if we split it into 3 equal arcs instead? So what if I put 2 points right here? And if I split 90 in thirds, we can see easily that this actually represents 30 degrees, and this then represents 60 degrees. But if I split pi over 2 into 3 pieces, we actually already saw the equivalence of 30 degrees to pi over 6 radians. And if that's pi over 6, it makes sense that this up here would be 2 pi over 6, which is pi thirds, which we've also seen there. And the other cool thing here is we can think about these guys' triangle as well. These guys connect with a 30, 60, 90 triangle, right? And we've already seen that if this has length 1 here, I guess I'll keep my color coding consistent, then this down here is going to have length 1/2, and I'll mark this one so we're not confused there. And then this guy here is going to have length √3 over 2. That's something we've established as well. So the coordinates of this guy here would actually be 1/2, comma, √3 over 2. And this guy's coordinates right here are going to end up being, interestingly, it's the same triangle, but it's just in a different orientation, right? And this guy's going to end up being with coordinates that are reversed from this. He now has a height of 1/2, and his overness, you could say, right, his x-coordinate is now the thing that's √3 over 2. So here's what I want you to do. I want you to now, on your own, take this unit circle and finish filling in all the equivalent angles that are just reflected over there around here. And the next thing I want you to do as well is not just the angles, I actually want you to, or not just the coordinates, but I want you to actually put their degree measures. Remember, this amount of space is going to cover 30 more degrees, but that's also going to give me, every amount of this space is going to give me pi/6 of a radian, right, of the arc length. Okay, so finish filling this out. Everything, degrees, radians, and coordinates for the rest of this circle, and then we'll move on to our next example.
All right, we're on our home stretch. This is where everything has been leading to. So now we can use the unit circle to find the exact sine and cosine values for the special angles or their multiples. Because we just looked at, in quadrant 1, you can find all those special angles from the special triangles, and then we can find the exact sine and cosine values and ratios. And as we learned recently, a shift in our thinking about sine and cosines, meaning sine can represent height, aka the y-coordinate along the unit circle, and cosine represents overness, aka the x-coordinate along the unit circle. So now that we have a unit circle with those special angles and their multiples all the way around in all the quadrants, we can find sine and cosine values from that. So why don't you go ahead and take a stab at that right now, since we have all the coordinates put along your unit circle, and we'll come back and look at the answers together. Go ahead and pause. Okay, let's look at the answers together. So, the sine of pi/6, if you go that much of an arc, right, around the circle, you'll see that the y-coordinate is equal to 1/2. 2 pi thirds, that's going to be over in quadrant 2. We go 1 pi third, then 2 pi thirds. And the cosine value is the x-coordinate, that's actually negative 1/2. The x-coordinates are negative in quadrant 2, right? How about the radian measure 3 pi? Well, 1 pi is halfway, so all the way is 2 pi. Then we go back again. It's going to be equivalent to as if it was just sine of pi, actually. They're not the same angle, but they have the same sine and cosine value, actually. So this is going to be the same as that, and that's actually going to have a y-coordinate of 0. And I want you to remember, this is the sine of pi. I'll just say same. And the last one here. Well, you may not have exactly known, like, wait, what do I do? What does it even mean to be negative? Well, here's what I want you to think. Remember how we talked about movement along the unit circle has always gone from the positive x-axis and it's gone counterclockwise. Well, a negative angle just simply means that we move the other direction. So if pi
3 pi fourths, if it was positive 3 pi fourths, would go halfway of 90 degrees, right? And then 2 pi fourths, and then 3 pi fourths, and it would be right there in quadrant 2, halfway between the y and negative x-axis, right? But this is negative, so I'm actually going to have to go down, down, and over here it's going to be in quadrant 3. And since in quadrant 3 both sine and cosine have negative values, and pi fourths happens to have equal sine and cosine, except maybe the positive or negative, then we know it's going to be negative root 2 over 2. Okay? And I want you to make note of something here. This is also the same as if we had gone around positively 5 pi fourths. Okay? So it's going to lay right there. So whether I go negative 3 pi fourths or positive 5 pi fourths, 5 and 3 make 8 pi fourths, which is 2 pi. So together that makes a full rotation, but they kind of complement each other. So this would actually be the same as, I'll write equals this time. It would be the same as if I had said cosine 5 pi fourths. Okay? So there's our lesson for today, and we're going to dive into a lot more of this stuff as we move along. Happy math. See you next lesson.